Hello. So I wanted to go through some of the data analysis that we're doing here on the first part of experiment 6. So I've ran a couple calculations. I want to go through how I might export some of the results. So I think this calculation here is the 1,3-dichlorobenzene isomer. So there it is. One thing I wanted to show is if you want to export this picture, which I think is worth doing, you might do a save image as. You just simply download the file. Whoops, that doesn't look right. I think I had better luck earlier by using the file save image. I just did the PNG format. Let's try this again. Yep, there it is. For some reason, I don't know what it is. If you right click on the screen, it's not working as well, at least on my end today. Interestingly, I think it worked better previously. So then, anyways, you can simply take a copy, simple copy of an image here. On my end, at least, I don't know what PCs are going to look like. I just was able to draw a box around the picture. I can then go over to Excel and should be able to, in a window, in one of the screens here, just paste this image, resize it. You can play around with the size of your cells if you want to make these a little bigger. But this might be a helpful way to store your pictures so that they're here. If you want to copy and paste these in your reports later, that might be helpful. So I'd gone through, let's just double check the 1,3 so I can show you where I'm getting these numbers from. So the 1,3 results are coming from, just scrolling down in your results. This is an HF631G star optimization frequency. Make sure you're doing the opt plus freak. And then I'm exporting this here, the RHF energy. This is my electronic. The internal energy really isn't useful. We're not exporting this value. Or if you did, you don't really need to do anything with the number, so it's not a big deal if you did export that number. But the enthalpy here would be the enthalpy of the molecule under the conditions that we didn't change off default. So it's going to be the enthalpy at whatever this temperature is here. So the number here, and copy the entire number. Just do a simple Control-C on the number, go over to your spreadsheet, and paste that in for your enthalpy at 298K. Okay, now these energies here are all in Hartrees per particle. The conversion to kJs per mole is 2625.5 kJs per mole per Hartree. So if we do that conversion, these are going to be humongous. These aren't going to directly compare to your values from NIST. Let me show you how you're going to compare the values from NIST, though. Let me show you one last detail, that being the dipole moments, just because I didn't export these earlier. That's just simply right here. I don't think we do too much with the dipole moment, but the dipole moments of some of these structures are kind of interesting. Like the 1,4-dichlorobenzene is going to go to 0, just because all the dipoles are going to oppose each other. Kind of chuckling. I don't know if you can hear my kids in the background. Okay, what is the other thing I want to show? Okay, so let's go into NIST for a moment and kind of see what we can find in the NIST webbook. So I have NIST open here, or at least the link I just searched, NIST Chemistry Webbook. Click on the results. Maybe just a formula search. So we're doing C6H4Cl2. Let's look and see what we see for the 1,2-dichlorobenzene. I want the gas phase. We're doing our calculations in the gas phase, so we're going to take the gas phase thermochemistry. Condensed phase would just be whatever the natural solid or liquid state the substance is at room temperature. So this would be like the solid phase. Actually, I think, I can't remember. I think 1,2 and 1,3 are solids at room temperature, but whatever the natural state is what the condensed thermochemistry data would be. So we're going to go to gas phase thermochemistry, and here's our delta HF. The standard enthalpy of formation here, 33.0 kJs per mole. We do a copy on this. Let's talk about this for a minute and why these numbers are vastly different from each other. I might have like a NIST section here, making a video, so please. Sorry. So I'm going to write my H298K. This is going to be the only thing I get a comparison on here. I'll paste my value in here. I don't like it that way. If we do a paste special match destination format, whatever. So 33.0. If I go, and that was the 1,2 isomer, not the 1,3. So let's just type it in. It's easier. So then we can go back. Look for the 1,3 isomer. That's here. Oh, one. I want the gas phase thermochemistry here. 28.1 kJs per mole. Okay, so these are the reaction enthalpies for forming these compounds from their elements in their standard states. So that would be the reaction of like 6 moles of like carbon solid in the graphite form, plus 2 moles of H2 in the gas phase, plus a mole of Cl2, which is a gas at room temperature. These things combining to form the 1,3, in this case, DClB, dichlorobenzene. And likewise, the 1,2 reaction would be forming the 1,2 isomer. Okay, I can double click and make these cells a little bigger, just to sort of show that the value that's a more negative or just smaller value is more stable. So there's less enthalpy associated with forming the 1,3 isomer. So from our literature data, or NIST data, the 1,3 isomer is more stable. And the difference was, and it's important to note, of course, the unit here, because these, I believe, were given in the units of kJs per mole. Okay, so the way you can say, well, how much higher in energy is this lesser stable 1,2 isomer? Well, let's do this. Let's just take the difference of the 1,2 minus the 1,3. It's already in kJs per mole. So the 1,2 isomer is 4.9 kJs per mole higher in enthalpy than the 1,3 isomer. And so we can essentially do those same calculations here. Now the only difference is these are in Hartrees per particle. So right now these are still in Hartrees, or atomic units. In the conversions given right on the front of your packet, the conversion to kJs per mole is 2625.5 kJs per mole. So we do that comparison, and you see the results are, at least in terms of sign, correct, and a little bit closer in magnitude. So the calculations are saying the 1,2 isomer is about 12 kJs per mole, less stable than the 1,3 isomer. Okay, so what we would be doing here is comparing also the 1,4s. You can throw in the results for the 1/4 or the structure in, kind of evaluate those. I'd mentioned in a video, and there was some discussion earlier if you were on the class Zoom feed. I do think the 1,3 actually is the most stable. I think 1/4 is slightly less stable than the 1,3. But again, that's kind of from my memory of the last time we did this procedure a while ago. But this is the basic idea of what we're comparing here. So we're looking up the gas phase. Make sure you use the gas phase thermochemistry data, because we're doing our calculations here in the gas phase. That's why we're choosing the gas phase thermochemistry data. Because those enthalpies are for forming the compounds from their elements at equal to 0. Let's actually discuss why, for a moment, the 33 and the 28.1 is so different from these values here. The computed enthalpies and the electronic energies, these are the absolute energies and enthalpies. These are not scaled in the same way that our standard enthalpies of formation are. In fact, it would be hard to scale this value to match this value here, because it's really hard to build solid structures. So the carbon solid really makes it tricky to evaluate or change or to do some sort of computational chemistry direct calculation of a referenced enthalpy of formation value. But what's easier is just, well, run your calculation on the 2 isomers with the same level of theory, same basis set, and then you can compare their relative energies. And then at that point, it doesn't matter what your reference state is. And so the only difference here is, well, what's the accuracy of our literature value? What's the accuracy of the experiments versus what's the accuracy of our computational chemistry calculations? So you can probably reason that as we improve our method, maybe go to a larger basis set, maybe we're going to improve this difference and get a little closer to the literature. But of course, the literature is also not exact either. So we shouldn't treat the literature as the exact value either, but rather it's, has some inherent impreciseness with it as well. So let's see if we get close to this value, but not necessarily directly dead on. But at least we're showing that the 1,3 isomer is more stable than the 1,2, matching the qualitative result from our literature comparison. So I hope that gives you a good way to get started and evaluate your results. So that's all for this video. Thank you.